Well, here we study Bernstein's theorem. So let us go to the statement of the theorem. So here is the statement, theorem. Bernstein's theorem. So here is the statement. Let A and B. So A and B are, these are non-empty sets. B to non-empty sets. So the theorem says that if there exists there exists a injective function from A to B and another injective function from B to A, then there exists a bijective function from A to B. Okay, so let me write. So if there exist injective functions, one from F from A to B and another from denoted by G from B to A. So these are injective functions. If there exist injective functions F and G, F from A to B and G from B to A, then the conclusion is then there exists a bijective function. There exists a bijective function H from A to B. So this is the theorem statement. So here we prove this theorem. So proof. So the idea of the proof of this theorem is following. So idea. So we would like to find a subset. Let me write. We would like to find a subset S of A, so that we may define, H equal to F on this subset. H equal to, or in other words, H of X equal to F of X for all X belongs to S. And so let me draw a picture. So suppose this is A and this is, let's say this is B. So this is A and this is B, and we would like to find a subset S. So suppose this is S, and from A to B we have injective function F, and from B to A we have injective function G. So on S we would, so suppose this is F of S. So this portion is A minus S, and this portion is B minus Fs. B minus F of S. And we would like to find a subset S, so that we may define H of X equal to F of X for all X belongs to S, and H is G inverse. H is G inverse on A minus S, and for such a subset we must have, so to get a well-defined function h. Okay. So what we need is following for such a subset. For such a subset S, we must have so G minus Fs, G of B minus Fs, G of B minus F of S. So G of B minus Fs. So this should image of this portion should be A minus S. So this is equal to A minus S, or equivalently S equal to S equal to A minus G of B minus F of S. Okay. So that is G must map B minus Fs onto A minus S. Okay. So now to complete the proof of this theorem, now it suffices to find such a subset S. Okay. Okay. So for the purpose, we define a function. We define a function we define a function denoted by, that is capital H, from P script P of A to script P of A. So what is this? This is nothing but the power set of A, that is script P of A. This is equal to the set of all subsets of A, that is equal to S belongs to S A. Okay. Set of all subsets of A. So we define a function h by h of S equal to this one, A minus G of A minus G of B minus F of S. So this is the function we define. Now to complete the proof, basically we would like to find a subset S of A so that this relation holds true. That is, and what is this? This is equal to H of S. So S equal to H of S. That is to complete the proof. To complete the proof, it suffices. So such a subset S is a fixed point of S. So it suffices to ensure that H has a fixed point. So now our goal is to show that H has a fixed point. So claim 1. So we claim, so this is our first claim about H. So H is increasing. So H is increasing. In the sense that if S subset of T and S comma T, these are subsets of A, So for S comma T belongs to power set of A with S subset of S implies H of S subset of H of T. So this is our first claim, and now let us prove this claim. Proof of claim 1. So what we have is subset of T. So let us draw a picture. So this is our A, and this is our B, and let's say uh, this portion is T, and this portion is f of T. Okay, and well, now S is subset of T. Let's say this is S, so S is included in T, and therefore f of S also included in f of T. So this is f of S. So this implies uh, f of S included in f of T. F of S included in f of T. Now notice that let me change the color. And so this is A and this is B, and from here to here we have function f, and from here to here we have function g. Now see this portion, this is b minus f of t. Okay, and this is sorry, this portion is b minus f of s. So b minus f of s contains b minus f of t, and therefore what we have, this implies b minus f of t is included in b minus f of s. And this implies g of b minus f of t included in g of b minus f of s. And by similar arguments, we have a minus g of b minus f of s. This is included in a minus g of b minus f of t, and this is nothing but h of s, and this is nothing but this is included in h of t. So this is equal to h of t by definition. So this is here is the definition. Okay, here is the definition of h. So this proves claim 1. This proves claim 1. Now we define the following. So let us define script C. This is the set of all subsets S of A. So S basically S belongs to power set of A. That is S is subset of A such that S is included in H of S. Okay. So this is subset of power set of A. Now, we define S tilde. Now, S tilde, this is equal to empty set if the script C, this is empty set. If script C equal to empty set. Else, we define S tilde equal to union of S over S belongs to script C. Okay. Now, we see that this S tilde is the least upper bound of script C. Okay. Then S tilde is the least upper bound of the sets S subset of A with S subset of H of S. Now, yeah, now we have the second claim which completes the proof. Claim 2, S tilde is a fixed point of H. H of S tilde, this is equal to S tilde. So now we prove claim 2, that will complete the proof of the theory. Proof. Claim 2. Okay, so what is S tilde? S tilde is defined by this. S subset of S tilde for all S belongs to script C. Okay, so basically S tilde is on the list. List upper bound. Basically, S tilde is defined by union of all elements. So let me recall here. S tilde equal to union. S belongs to script C. Union of all S belongs to script C. So therefore, S subset of S tilde for all S belongs to script C. Now H of S subset of H of S tilde. Okay, and so this implies, and S subset of H of S, because S belongs to script C, and which is again subset of H of S tilde, and this implies, so this happens for all S belongs to, and this happens for all S belongs to script C, and therefore we have union S belongs to script C. This is subset of H of S tilde, and this is nothing but S tilde. So therefore we have S tilde subset of H of S tilde. Okay. So this is, so in particular S tilde belongs to script C. Now H of S tilde, so this implies S tilde belongs to script C. Now H of S tilde subset of H of H S tilde. Okay, so this implies h of S tilde also belongs to script C, and this implies, and by definition of S tilde, this implies h of S tilde subset of S tilde, because S subset of S tilde for all S belongs to script C. In particular, here what we have, h of S tilde belongs to script C, so h of S tilde is subset of S tilde. So this is the second inclusion. So now inclusion 1 and inclusion 2 together imply h of S tilde, this is equal to S tilde, which is what we wanted to prove. So this completes the proof of Bernstein's theorem. So before we stop, let me give an exercise. Uh, so using Bernstein's theorem, so show that there exists a bijective function f from Rn to Rn, or enough to show that alternatively, show that there exists a bijective function. So let me denote by something else. H from R to Rn. So this is R is set of reals and Rn the set of all n tuples of reals. Okay. So that's it. So let me stop now.